All right, guys, welcome back. We are going to review 3.5 and we are going to work through 3.6b, rational inequalities, in this video. Just a warning, it is spring 2020 pandemic time, so I have moved home and I have rigged a stand for my Surface Pro to do these videos on cardboard boxes. So we're just doing the best we can, make and do, and we're going to see what we can do. All right, review of 3.5 rational functions. Where do you look to figure out if you have vertical asymptotes and or holes in the graph? Well, that is determined by expressions in the denominator. Expressions in denominator. Sorry, my space between the boxes is small. Denominator. All right, there we go. Expressions in the denominator. What makes the difference between whether that expression in my denominator gives me a vertical asymptote or a hole? Well, if it is in lowest terms, it gives me a vertical asymptote. If it can factor out, or cancel, because it's not in lowest terms, it represents a hole in the graph. For example, if I had x minus 3 over x minus 3 times x plus 5, x equals 3 is a hole because it's going to factor out, and x equals negative 5 is a vertical asymptote because it stays put. It's a value that's excluded from the denominator, that it's still there when my function is in lowest terms. All right, where do I look to figure out whether I have horizontal or slant asymptotes? I look at the degree of the numerator, and I compare that to the degree of the denominator. I compare it to the degree of the denominator. If the degree of the numerator is greater than the degree of the denominator, and we're going to say greater by 1, because we are limiting ourselves to linear asymptotes. If the degree of the numerator is greater than the degree of the denominator by 1, then I have a slant asymptote, and I have to do long or synthetic division to figure out that equation. If the degree of the numerator is less than the degree of the denominator, then I have a horizontal asymptote at the x-axis. And so my equation is just y equals 0. And finally, if the degrees are equal, then I have a horizontal asymptote still, but it is at the ratio of the leading coefficients. At the ratio of the leading coefficients. For example, if f of x equals 3x squared plus 5 over 7x squared minus 12, I have a horizontal asymptote at y equals 3/7 because that's my ratio of my leading coefficients. Okay, the next 4 problems, we are going to write the rational equation. We're going to use the information we have, and we're going to simplify and write that rational equation. Our first problem states we need to find the rational function that passes through the point 3,1, has the x-axis as a horizontal asymptote, and the line x equals 1 as its only vertical asymptote. Well, we have some information here. We have a point, an xy ordered pair, that we know our graph goes through. We know we have a horizontal asymptote at the x-axis. That means that we know the degree of the numerator is less than the degree of the denominator. And we know that we have x equals 1 as our equation for the only vertical asymptote. So let's start building our function. F of x, rational function, so we have our division bar. Denominator gives us vertical asymptotes or slant asymptotes. Vertical asymptotes or holes. Since x equals 1 is a vertical asymptote, if I move that over, that gives me the expression x minus 1 in my denominator. Now, horizontal asymptote at the x-axis means the degree of the numerator has to be 1 less than the degree of the denominator. Well, if the degree of the denominator is 1, that means I can't have a variable in my numerator because that degree needs to be less than. So I have to figure out what constant goes in my numerator. Well, I know when x is 3, y is 1. F of x is the same thing as y. So we're going to say y, or 1, is equal to this, where x minus 1 is this expression, and we have 3 to plug in to x. Well, that is equal to whatever this missing value is. 3 minus 1 is 2. So we have 1 equals something over 2. To solve for this missing term, I'm going to multiply both sides by this denominator, which gives me my missing term is 2. That's my equation, f of x. All right, let's do the next one. Reason through this one with me. Rational function passes through a point, so we have an xy ordered pair. So we can plug in y and make it solve for x, plug in x, make it solve for y is 4. Y is 0 as its horizontal asymptote. That's my x-axis again. So we know again the degree of the numerator is less than the degree of the denominator, and x equals 3 is the only vertical asymptote. So we have the same situation as we did for number 1. Let's name this one g of x, and we've got some constant in the numerator. My denominator gives me this vertical asymptote, so that denominator is going to be x minus 3. Remember, we said this has to be a constant because I know my horizontal asymptote is the x-axis. That only happens when the degree of the numerator is less than the degree of the denominator. So that means my degree of my numerator has to be 0. It has to just be a constant up here. G of x is the same thing as y. If I plug in these values, that means y would be 4. I've got something over, x is 0, so 0 minus 3. So I've got 4 over a negative 3. I'm going to work through and solve that equation. 4 equals something over negative 3. To solve for this unknown, I have to multiply by both sides by negative 3. And here I get that my numerator has to be a negative 12. All right, let's look at the next one. A rational function passes through the point. So there's an xy ordered pair for me to check. Y equals negative 2 as the horizontal asymptote. So it's still a horizontal asymptote, but it's not the x-axis. Well, horizontal asymptote, not the x-axis, happens when the degree of the numerator is equal to the degree of the denominator. X equals negative 3 is the only vertical asymptote. This x equals negative 3 gives me my denominator. Let's make this h of x. My denominator this time is going to be x plus 3 because we need to move that back over to find the expression. And then I know I need an x in my numerator because it needs to be degrees are equal. So I need x over x. So it's first degree over first degree. I also need to know the ratio of my leading coefficients needs to be negative 2. Well, if I keep this simple, this is a 1. I can put that negative 2 right there. All right, the last thing that I need to check is to make sure that it goes through this point. So I've got a missing value that I want to add or subtract here. I need to figure out what goes there to make this true. Well, h of x is the same thing as y, so that would be 2 equals negative 2x plus something over x is negative 1 plus 3. So let's simplify this. That gives me 2 equals negative 2x plus something. Negative 1 plus 3 is 2. Now, work through this. I need to clear out this denominator by multiplying both sides. So I'm going to multiply both sides by 2. That's what I've been doing all along. Now I move up here to get more space. 2 times 2 is 4. 4 is equal to negative 2x plus something. Well, what makes that, negative, my x, I didn't plug in my x. I did it in my denominator, but not my numerator. So that should be a negative 1 as well. Negative 2 times negative 1 is a positive 2. If I subtract that 2 from both sides, I get 2 equals that unknown value. So plus 2. There's my rational expression, rational function. Okay, I apologize for messing that one up, guys. Let's look at number 4. Let's talk through number 4. Don't panic. You're not going to have to do this on the exam. This is just a really good way, was going to be a really good way for us to work through focusing on this concept while we were in class together. So we've got f of x, g of x, h of x. Let's just name this one k of x. We have a point. We have a horizontal asymptote, not at the x-axis, so we know that our degrees are going to be the same. And then we have a single vertical asymptote. So we start with the same setup. We have x plus or minus something up here. We have x minus 2 as my denominator. Since the horizontal asymptote is at 1, that means 1 over 1 is 1. You know what? I could throw other coefficients in here. 2 over 2, 3 over 3. That's always going to give me that horizontal asymptote at 1. But we're just going to keep it as simple as possible. So we're just going to leave it like it is. Okay, now we need to plug in 0 for both of these x's, not just one, like I messed up in the previous problem, and plug in 5 for y. K of x is the same thing as y. So that's 5 equals, well, x is 0. 0 plus something over 0 minus 2. Well, that gives me 5 equals my unknown over negative 2. And remember, here's where we multiply both sides by that denominator. So if I multiply both sides by a negative 2, I get negative 10 equals my unknown. So this is x plus a negative 10, or I could rewrite that just to say x minus 10. Either way is fine. Okay, that kind of reviews the concepts, those basic concepts of our things that we learned in 3.5. Let's go through and start talking about solving rational inequalities. Now, you guys already solved polynomial inequalities. You were able to use graphing to check, but we don't want to take the time to graph all of our rational functions in order to simplify and figure out the inequalities. You also know how to check them when you are looking at the graph. So we are primarily going to be focusing on when we don't have a graph to look at. Okay, first things first, rewrite the inequality so that 0 is on one side and a single ratio in lowest terms is on the other. Then find all the zeros in both the numerator and denominator. Zeros in the denominator represent vertical asymptotes. Their values where the function is undefined. It can never be equal to that because it's undefined. Zeros from the numerator, however, represent function values. Function values of 0. So that could be included. For example, where my inequality symbol here is or equal to, I can include any zeros that come from the numerator because that is a function value of 0. I couldn't, however, include zeros from the denominator because that's a place where the rational function is undefined. Okay, first example. Find the intervals that satisfy the following inequality. Well, it's already set to 0. And I have a single ratio in lowest terms on the other side. So I am going to jump right in and identify those zeros and place them on the number line, after which I will test a point in each interval. Okay, so let's get our number line out there. Number line. I've got a 0 from the numerator. 0 from the numerator, x plus 3 equals 0. 0 from the numerator, x equals negative 3. That's where I have a function value of 0. And then I've got denominator. I need to factor this. That's difference of squares. It factors out to give me conjugate pairs. So that gives me a negative 1 and a positive 1. Those are zeros from the denominator, so those are places where the function is undefined. So I'm going to mark those with a U. All three of those values, all three of those zeros need to go on my number line from least to greatest. So I'm going to mark negative 3, negative 1, and 1. When I put three values on my number line, I have divided it up into 4 intervals. I have to test a point in each one of those intervals. So I need to test 4 points. Unlike with polynomial functions, I cannot predict behavior for my rational inequalities, so I need to actually make sure I test a point in each interval. 0 is always easy to test, so I'm going to find where 0 goes and test that. The only integer between negative 1 and negative 3 is negative 2, so I'm going to test that in this interval. For these n's, I always go big. Now, big can look like 10, big can look like 100, totally up to you. Let's do 100 just because it's fun. Now, for each interval, I'm interested in whether or not the values in that interval, when I plug in this x, do the y values come out as positive or negative? So I'm not interested in what the y value is when x is a negative 100, negative 100 over here on the left. I'm interested in, is that y value positive or is it negative? Okay, so I'm going to think about plugging things in and checking. And when I plug in, I'm just going to plug in right here. Well, if I plug in x equals a negative 100 into this inequality that I was given, x plus 3 over x squared minus 1. Negative 100 plus 3, that numerator is negative. It's actually a negative 97, but that doesn't really matter. What matters is this negative out front. Then in my denominator, I have a negative 100 squared. Well, when I square that, it becomes positive. So 100 times 100 is actually 4 zeros minus 1. That denominator is definitely a positive denominator. So when I plug in x equals 100, I get a negative over a positive, which is negative. So this interval, all the values in that interval are negative values. Okay, let's do our next interval. Let's check and see what happens when x is equal to negative 2. Well, if I plug in a negative 2, I have negative 2 plus 3, and then in my denominator, negative 2 squared minus 1. I don't care what the values are. I care whether they're positive or negative. Negative 2 plus 3 is a positive 1. In my denominator, I have 4 minus 1, which is positive. I can go ahead and write that down. That's a positive 3. Actual value doesn't matter. Positive is what matters. Zeros. Zero is always easy. So where x is 0, what happens? I've got 0 plus 3, 0 squared minus 1, positive over negative. Positive over negative is negative. That interval has negative y values. It's going to fall on the graph below the x-axis. Okay, so 100, where x is a positive 100, 100 plus 3 over 100 squared, well, that's obviously going to be positive. Positive over positive is a positive interval. Now, we talked about the fact that it matters whether we have a 0 or an undefined value, but we didn't mark it. X equals negative 3 is a value of 0, but x equals negative 1 and x equals positive 1 are places where my functions are undefined. So I am not going to include either of these endpoints. But since I have we're equal to, I can include this endpoint. This inequality symbol reads as greater than or equal to, so I'm looking for positive intervals. These two intervals are positive. They satisfy my inequality. This first interval is from negative 3 to negative 1. I can include the negative 3 because it's a value of 0. I can't include the 1 because it comes from the denominator and it represents a place where the function is undefined. This interval is from 1 to positive infinity, and again, I can't include the 1 because it comes from the denominator where the function is undefined. All right, let's do this next one. What if this inequality was written as x plus 3 over x squared minus 1 is less than 0? Now, I didn't change what I just worked with. What I changed was my inequality statement. Now I'm interested in the values where we are less than 0. So I want the negative intervals, and it's not including. So no square brackets. Well, if these are my positive intervals, these two are my negative intervals. When I write out that, it looks like negative infinity up to negative 3, not included this time, or negative 1 to 1. All right, I started to say any questions, but you guys are not here to ask me questions. I missed that. All right, let's see what's next. Another example of our inequalities. Now, for this one, we are not set to 0. So the very first thing I need to do is rewrite this inequality so that it is set to 0. When I do that, I move that 1 over. So my starting place is to say 2x over x plus 1 minus 1 greater than or equal to 0. Now I've got it set to 0. I need to take this 1, I need to write all of this as a single term. Right now it's at 2 terms. I need to write it as a single term with a common denominator. So I need to multiply by that well-chosen 1 where I multiply in the denominator. Sorry, I had to squish. X plus 1 over x plus 1. That's just 1. I chose it because that's my denominator. It gives me a common denominator. So I have a common denominator. I can write it as one expression. I have 2x minus x minus 1 greater than or equal to 0. Simplify my numerator. 2x minus x is x minus 1 over x plus 1, where that is greater than or equal to 0. That's the simplified inequality that I'm working with. So I need to find my boundary points, and I need to graph them on a number line. I have two boundary points. I have a 0 from the numerator, and I have a 0 from the denominator. If I set my numerator equal to 0, I get 1. And that's a 0 from my numerator, so it is an actual function value of 0. If I set my denominator equal to 0, I get negative 1. Because that's a 0 from my denominator, that's a place where my function is undefined. It represents the equation of a vertical asymptote. Okay, two boundary points give me 3 intervals. I need to test a point in each of those 3 intervals. 0 is in the middle. That's always easy to test. And then I'm going to go big for both ends. We did 100 last time. Let's just do 10 this time. And let's check these 3 test points. Well, where x is equal to negative 10, I'm going to use the simplified inequality because that's the best way, the easiest way to do it. That would be negative 10 minus 1 over negative 10 plus 1. Well, that's a negative 11 over negative 9. What really matters here, negative over negative, is positive y value for that interval. If I plug in 0, where x is 0, into this inequality, that would be 0 minus 1 over 0 plus 1. That's a negative 1 over a positive 1. That is a negative result. So every y value in that interval is negative. My function would fall below the x-axis here, above the x-axis there. Final, x equals positive 10. Well, 10 minus 1 over 10 plus 1 is going to be 9 over 11. That is positive. So all of those y values are going to be positive. My inequality statement asks me for where my function is greater than or equal to 0. That's my positive intervals, so those two ends. Or equal to means I can include the boundaries that are a 0 function value. Can never include those undefined function value boundaries. So the intervals that satisfy this inequality are negative infinity up to not including negative 1, or including 1 to positive infinity. That's my solution set for this inequality, rational inequality. Okay, let's do another one. Find the intervals that satisfy the following inequality. Very first step, I have to set it to 0. That means I'm going to have to move that 3 to the other side of my inequality symbol. So I've got x plus 4 over 2x minus 1 minus 3. And I'm going to go ahead and write that 3 over 1 because I know I'm going to have to create that common denominator. And so it's easier for me if I keep things as rational expressions right from the start. Then I multiply in my denominator that I need. My denominator I need is 2x minus 1. So I multiply that in over itself. That's my well-chosen 1 that I'm multiplying by. When I do this, I have a common denominator of 2x minus 1. So I can just rewrite the entire function as being over 2x minus 1. Now let's look at our numerator, x plus 4. This negative 3 needs to distribute in. Negative 3 times 2x is a negative 6x. Negative 3 times negative 1 is a positive 3. Now I simplify by combining like terms. X minus 6x is a negative 5x. 4 plus 3 is positive 7. My denominator is 2x minus 1, and I've got that greater than or equal to 0. Well, this doesn't factor, so I have a single rational expression in my numerator and a single rational expression in my denominator. So I'm going to have 2 boundary points to mark on my number line. I need to figure out what those values are by setting my numerator equal to 0 and then my denominator equal to 0. So if I take my numerator equal to 0, negative 5x plus 7 equals 0, I get a positive 7/5. And then that is a function value where my function is equal to 0. Now what about where my function is undefined? That comes from the denominator. So I set that denominator equal to 0 and I solve. I get positive 1/2. Well, I need to put these in order. That's the place where my function is undefined. That represents a vertical asymptote. I need to put these in order on my number line. Which one's less? Which one's greater? Well, 1/2 is less. 7/5 is more than 1. It is greater than 1/2. 2 boundary points means 3 intervals to check. 0 this time is over here. We're going to go ahead and do 100 again, just for fun over here. What falls between 1/2 and 7/5? Well, 1 falls. 1 is a nice integer that falls between those two fractions. So those are the values that we can check to see where our function, where our inequality statement is greater than or equal to 0. So we're looking for those positive intervals. Okay, what if x equals 0? If x equals 0, and I'm again going to use my simplified version. If x equals 0, 0 times -5 is 0. That gives me a numerator of 7. 2 times 0 minus 1 is a -1. So that is a negative interval. What if x is 1? Well, if x is 1, my numerator is -5 times 1. That's -5 plus 7. My denominator is 2 times 1 is 2 minus 1. That gives me a 2 over 1, which is positive. That interval is positive. And then finally, I've got 100. What if x is a large, positive large, 100? Well, that's -500 plus 7. -500 plus 7 is a negative value. It's -400 and something, right? -493. But that doesn't matter. What matters is it's negative. And then in my denominator, 2 times 100 is 200 minus 1 is a positive 199. A negative divided by a positive is a negative. So that interval is negative. We have our 3 intervals. We stop and think, okay, what are we looking for? We're looking for greater than or equal to. That is my positive interval. This 1/2 came from the denominator. My function is undefined there. So I can't ever include that. This positive 7/5 came from the numerator, so it's a value of 0 there, so I get to include that boundary point. So my interval that satisfies my inequality is 1/2 not included to 7/5 included. So parenthesis, square bracket. Okay, we have 2 practice problems here that we want to go through. Rather than going through them and talking through them, I'm going to work them out quietly. I want you guys to do it on your own. Pause the video now and then come back and check and see how you did. All right, for this one, I'm not showing you plugging in the values that I check. I'm just going to show you the result. For this example, you have to simplify first. I'm going to just give you that simplified inequality. That simplified inequality when I set it equal to 0, because remember you have to move that 2 over and find that common denominator. What you should get is negative x plus 7 over x minus 2 less than or equal to 0. That is the inequality that you are trying to satisfy. The zeros that gives you from the numerator and the denominator That gives you a positive 7 in the numerator and a positive 2 in the denominator. So 2 is undefined, 7 is a function value of 0, and I need to check 3 intervals to see where I'm positive and where I'm negative. I can do 0, anything between 2 and 7. I'm going to choose to do 5 and 10. When I check those values into this inequality to see what's positive, what's negative, I get negative, positive, negative again, because I'm interested in those negative, less than or equal to. I'm interested in those negative intervals, so I'm interested in the ends, not the middle. Cannot include 2 because it is a 0 that comes from the denominator. I can include 7 because it's a function value of 0 because it comes from the numerator.